Welcome back, friends. This is Dr. Rajesh Borole. Today we are studying full wave bridge rectifier. The circuit diagram of full wave bridge rectifier, which converts AC into DC power, is shown in figure. Here in the circuit diagram, it is shown that there is a step down transformer T1 and secondary winding feeds the diode bridge. There are four diodes D1, D2, D3 and D4. Function of this diode is to rectify the secondary AC signal to the unidirectional DC voltage across the load. Let us see how it will do it by understanding its operation. Let us see the operation of the circuit and the waveform at various points in the circuit. Here, the first waveform shows the secondary voltage VAB, that is Vm sine of omega t, with the positive half cycle from 0 to pi and the negative half cycle from pi to 2 pi. Let us see the operation during positive half cycle. See here the figure number 2. During positive half cycle of the input, that is from the interval 0 to pi, VAB is positive at A and negative at B. And therefore, the diode D1 and D2 gets forward bias, whereas D3 and D4 gets reverse bias. And therefore, diode D1 and D2 acts as on switches, whereas D3 and D4 are in off state. They are open circuited. And the current is flowing from the secondary winding from point A via D1 from the load resistance top end to bottom end, then via D2 and back to the negative terminal of the secondary winding. And in the secondary winding, the current is flowing from point B to A. Since diode D1 and D2 are in on state, they will connect the voltage VAB across the load. And therefore, if you see the load voltage waveform, here the second waveform, during the positive half cycle, the interval 0 to pi, you will see that the load voltage waveform is same as the input voltage waveform. Whereas, if we consider the practicalness of the diode, then the output voltage is slightly less than the input voltage VAB by the voltage drop across diode D1 and D2, and some voltage drop across the secondary winding, which is very small compared to the output voltage. And therefore, for most of the practical applications, we will consider that voltage across load is same as the voltage VAB during the positive half cycle, that is Vm sine of omega t, as shown in the waveform also. During negative half cycle of the input now, that is the interval from pi to 2 pi, we will see by referring this third diagram, VAB is negative, that is VBA is positive. B terminal is positive with respect to A. And therefore, diode D3 and D4 gets forward bias and they are going in on state. Whereas diode D1 and D2 goes in off state because they are back biased. And therefore, the current is flowing from the secondary winding from terminal A to B from B to diode D3, again from top end of the load resistance, then via diode D4 and back to the point A. So therefore, again during negative half cycle, the VBA is connected across the load and VBA is the inverted cycle of VAB, and therefore during negative half cycle we will get the inverted positive half cycle across the load as shown in the figure. Therefore, the operation we have seen from a complete interval 0 to pi, we get two positive half cycle in the output. Thus, we can say that this circuit rectifies both the half cycle of the input as positive half cycle at the output. You can get both the output half cycle as negative half cycle if we change the direction of the diode in the bridge circuit, and that results to negative rectifier circuit. Now let us consider the current waveform. If the voltage waveform is denoted by Vm sin of omega t from the interval 0 to pi, then current waveform is similar because load is resistive, and it is given by Im sin of omega t, whereas Im is Vm divided by the loop resistance, that is the resistance of the secondary winding plus resistance of the two diodes, say D1 and D2, so that is twice Rf and the load resistance, and therefore Im is equal to Vm divided by Rs plus twice Rf plus RL, and that is the peak value of the load current, and the wave shape is analogous to the voltage wave shape. Whereas if you see the current through the diodes, you will find that every pair of diodes, say D1 and D2 as well as D3 and D4, only conducts the current during the respective half cycle. If you see the voltage across the diode D1, when D1 is on, or during the positive half cycle when D1 and D2 are on, here only voltage across D1 is shown. Similar will be the voltage across D2. So during positive half cycle, since D1 is on, voltage across it is ideally 0. Practically it is 0.7 volt. And during negative half cycle, since diode D1 as well as diode D2 are in reverse bias, therefore voltage across diode D1 is same as VBA, and that is nothing but the negative half cycle Vm. That's all about the operation. Let us now find out the various performance parameter, and let us compare this rectifier with the previous configuration we have studied. Here in the figure, I have repeated the waveform of the load current for the sake of simplicity. Now, from this current waveform, we can represent the current waveform as Im sin of omega t from the interval 0 to pi. Similarly, the current is again Im sin of omega t from the interval pi to 2 pi, and that is the load current. Whereas the Im value, that is the peak value, is given by Vm divided by Rs plus twice Rf plus RL. Now let us estimate the average load current ILDC. The average load current ILDC is given by the average value formula, that is ILDC is equal to 1 by pi 0 to pi Im sin of omega t d omega t. Im is constant, so taken out from the integral sign. Sin of omega t integral is minus cos of omega t, and the limits are from 0 to pi. Substitute the limit. We will get ILDC is equal to minus Im by pi cos of pi minus cos of 0. This bracket is evaluated to minus 2. And therefore, after simplification, you are getting the average load current ILDC as twice Im by pi. The second parameter is average load voltage VLDC. It can be simply obtained by using the Ohm's law. VLDC is equal to ILDC into RL, whereas ILDC is equal to twice Im by pi that we have derived in the first equation. So therefore, VLDC comes out to be twice Im by pi into RL, where Im is Vm divided by Rs plus twice Rf plus RL. Since Rs plus twice Rf is much less than RL, if that is the case, then VLDC can be approximately twice Vm by pi, which is same for the center tap full wave bridge rectifier. Now RMS value of the load current we will find out, and it is denoted as ILRMS. It is the RMS value, that is root mean square value, and it is defined as the mean of square of the function under the radical sign. So therefore, here function is Im sine of omega t. So square of Im sine of omega t is Im square sine square omega t. And the average value is given by 1 by pi integral 0 to pi Im square sine square omega t d omega t. And the RMS value is the value under the radical sign as 1 by pi integral 0 to pi Im square sine square omega t d omega t raised to half. Solve this equation. Since sine square omega t is 1 minus cos of 2 omega t by 2, then solve the integral and substitute the limits. So we get under radical sign Im square by 2 pi in bracket pi minus sine of 2 pi by 2, and that simplifies to Im by root 2. So ILRMS is estimated to be Im by root 2, where Im value is same as what we have mentioned earlier. Now, the RMS value of the load voltage. Since we know the RMS value of load current, if we multiply it by the load resistance, then we will get the RMS value of the load current as per the Ohm's law. So VLRMS is equal to ILRMS into RL. Substitute the value of ILRMS here, and that gives VLRMS is equal to Im by root 2 into RL. Whereas Im is Vm upon Rs plus twice Rf plus RL. Here there is a typo. Only Rf is shown. It is twice Rf. And since Rs plus twice Rf is much less than RL, therefore the value of RMS voltage across the load comes out to be approximately Vm by root 2. Now let us estimate the ripple factor, and ripple factor is defined as R is equal to RMS value of the AC component at the output divided by DC component, and that is equal to the ratio of under root VL RMS square minus VLDC square divided by VLDC. Substitute the values of these terms and simplify. We will get the ripple factor equal to 0.482, that is 48.2%. So it indicates that this rectifier converts the AC signal into DC signal with 48% unwanted ripple component at the output. Compared to half wave rectifier, this is much better because in half wave rectifier, the ripple factor is 121%. So therefore, full wave rectifiers are normally used in practice because their ripple content are less. Now let us estimate the efficiency of conversion of this rectifier. And for that purpose, as we know, the definition of efficiency is eta is equal to the ratio of output DC power and the supplied AC power. And therefore, we have to estimate the output DC power and supplied AC power. So in the expression 6, we will estimate the output DC power as PLDC equal to ILDC square into RL. ILDC is already estimated in step 1 and that is twice Im by pi. Therefore, PLDC comes out to be twice Im by pi square into RL. Similarly, the AC input power as denoted by PAC is equal to IS RMS square into RS plus twice RF into RL. Whereas RS plus twice RF is much less than RL, therefore it will be ignored. PAC is therefore estimated to be Im by root 2 square into RL. Now from equation 6 and 7, we will estimate the rectification efficiency eta as the ratio of DC power output to AC input power, PLDC by PAC. Substitute the values of PLDC and PAC. We estimate that efficiency is around 0.811, that is 81%. It means that this rectifier is capable of converting AC power to DC power up to 81% and only 19% power will be lost. Compared to half wave rectifier, it is far better efficiency because in half wave rectifier, the rectification efficiency is coming around 41%. And therefore, losses are more in half wave rectifier compared to the full wave rectifier. Now let us estimate the transformer utilization factor. TUF, and that is defined as the DC power output divided by VA rating of the secondary. That is the ratio of PLDC to PSRMS. Substitute the value of PLDC and PSRMS as twice Vm by pi into twice Im by pi divided by Vm by root 2 into Im by root 2. That comes out to be 8 by pi square, that is 81.1%. So transformer utilization is also coming out to be 81%, which is even far better than the full wave rectifier using center tap transformer, which is around just 57%. It indicates that the transformer resources are effectively utilized compared to the center tap full wave rectifier. And therefore, the bridge type of configuration of full wave rectifier is more popular in practice since its transformer utilization is also good as well as it only needs a single secondary winding transformer and therefore the bulkiness of the supply section will be less. And that's why the bridge rectifier will be the obvious choice for electronic circuit power conversion stages. The peak inverse voltage PIV value is Vm in this circuit and the ripple frequency Fs is 100 Hz as observed from the waveform. Here in the table, we have compiled all the various parameters we have just estimated for half wave rectifier, full wave rectifier and bridge rectifier for comparison purpose. And that's all for today, friends. Bye bye.